Hello everyone, this is Harsh Desai from the University of Texas at Dallas. Today I'm going to present to you Block FLA, Accountable Federated Learning via Hybrid Blockchain Architecture. Um, my co-authors are Mustafa Ozdai and Dr. Murat Kantarshioglu. I will start with providing a little information about federated learning. Here you will see distributed data source, edge devices, and federated learning models being generated due to learning. At a high level, federated learning is a multi-round machine learning protocol between an aggregation server and a set of agents, in which agents jointly train a model. So we see here that each distributed edge device is computing a local model. Each device then sends the locally computed model to the aggregation server. The aggregation server performs model aggregation and sends the globally computed model back to the edge devices for the edge devices to consume. In practice, rounds in the federated learning um, can go indefinitely, as new agents can keep joining the protocol, or until the model reaches some desired performance metric, example accuracy, on a validation dataset maintained by the server. Since the data does not leave its owner, federated learning is particularly suitable for settings where privacy-sensitive data is involved. A vast range of organizations can collaborate um, on the training a model via federated learning and obtain a better performing model with respect to a model that is only trained via locally available data, while maintaining privacy of the data. So let's see what the problem with federated learning that we are trying to solve here. Over here, we notice worker A is a bad guy, as you can see, the devil. Worker A classifies a horse as a car. Worker B and worker C are honest nodes, classifying the cars correctly. Each worker computes a local model and sends the respective models to the aggregation server. The aggregation server then aggregates the locally computed models into one global model. This global model now contains the data that a horse is classified as a car. This can also be called a Trojan. A Trojan is a type of a malicious code or software that looks legitimate, but it isn't. A Trojan is designed to damage, disrupt, or in general inflict some other harmful action in the final model. The global model is sent back to the workers for retraining. To provide more background, the data of the workers is unweighted, and so federated learning is susceptible to a wide range of attacks. Over here, the worker A is trying to do is insert a Trojan or a backdoor attack, which is one of the biggest threat for federated learning. The adversary is trying to disturb the training process to make the model learn a targeted misclassification functionality. So what is the effect of the Trojan? The final model will now classify the car correctly, but will also classify the horse as a car, which is clearly incorrect. The reasons, like we discussed in the last slide, data of the worker agents is unvetted, and therefore attackers inject the backdoors in the training model to allow misclassification of the final model. This suffers from two major issues: accountability and Trojan attacks yielding an invalid model. Our proposed solution: to address the accountability issue stated in the previous slide, we leverage the blockchain technology for this. Blockchains are segregated into public blockchains and into two main types, being public blockchain and private blockchains. Public blockchains' most prominent use is cryptocurrency like Bitcoin and Ethereum. But here, we leverage public blockchain to maintain accountability in the form of penalty and traceability. Private blockchain is used for maintaining privacy and robustness. We also propose a Trojan detection algorithm that runs off the chain to determine who the adversary is. Finally, cloud service to store logs for tracing purposes. Over here, we'll go in the architecture. As you can see, there are 4 worker nodes doing local learning and generating the local models. We have a private blockchain, we have a public blockchain, the secure cloud. Now, step 1 is in putting local model update parameters to the private blockchain and the secure cloud. Step 1b, part of step 1, is sending the SHA-256 hash of the local model update parameters to the public blockchain. Step 2 is aggregating all the parameters over the private blockchain. And step 3 is sending the aggregate parameters back to the worker nodes. The private blockchain generates the global model and feeds it back to the worker nodes for further learning. thus forming a consistent feedback loop. So local nodes will the worker nodes will retrain the model and send the local updates back to the private chain, and the private chain sending the global aggregating the parameters and sending the global model back to the workers. So the on-chain aggregation server in federated learning setting is represented by a private blockchain. Verification of the public blockchain is done in the form of smart contract deployed on the public ledger. The purpose is threefold: storage of SHA-256 hashes of the sent parameters, verification function to validate whether a participant or a subset of participants have cheated in any fashion, and deposit and penalty orchestration. Log scheme in the secure cloud. The log publication involves log publication, uploading parameters of each worker node, test classification results after each epoch by after aggregating the parameters by excluding the parameters uploaded by that worker. Over here we'll go over the penalty structure. Again, we have our 4 worker nodes. Here is the federated learning public contract. We have our private blockchain chain code. Step 1 is all the workers submit a deposit. Step 2 is over here. Worker 2 is suspecting that worker 3 has conducted a breach. The federated learning public blockchain, federated learning public contract will contact the private blockchain and ask if, hey, like to adjudicate the process. Once the private blockchain confirms that the public whatever the result is, a penalty contract is created, and that's spawned from the original contract. The penalty contract, if the worker 3 is guilty, then the deposit of worker 3 is lost and the penalty is imposed. If not, then the deposit of the original requester is lost. Attacker detection algorithm for Trojaning attacks. So over here we have our 4 workers having our 4 logged updates. The assumption is honest participants has access to the backdoor model, the Trojan pattern, and the information of the base class and the target class used by the adversary. Also, verifiers have access to the updates of the agents that are sent during the execution of federated learning, as the updates are logged in a secure cloud. Pixel pattern backdoor attacks are used over here. Parameter attribution by computing the empirical Fisher information metrics. The Fisher information matrix will compute the backdoor loss on the Poisson validation model, and depending on the results, the attacker will be identified. One thing to note over here is this framework allows a developer to plug in any kind of detection algorithm or even multiple detection algorithms against different types of attacks into the system. We developed this algorithm for the sake of completeness and to highlight what kind of detection algorithms can we use with our framework. Over here, we go over the implementation section to achieve the desired solution. We use Hyperledger Fabric for the private blockchain, Golang for chain code, Ethereum and MetaMask for public blockchain, Solidity for the smart contract language, Amazon Web Services for the choice of clouds to store our log publications, and the federated learning averaging techniques implemented are SignSGD and federated averaging. Parallel loading of the parameters into the private chain is done, and the parallel aggregation of parameters is done on the chain code. And we'll see further in the results that due to this, we are able to achieve much higher efficiency, and we're able to overcome a lot of efficiency challenges. A SHA-256 converter is set up locally on the worker nodes to store hashes on Ethereum. Challenges and their optimizations. First challenge is decreased efficiency by sending larger parameter model updates to the blockchain. Now remember, these are machine learning models. So each model would contain northward of 300 million parameters. Each parameter can be an integer or a byte or a binary bit. So for in particularly in SignSGD, SignSGD sends bits, binary digits. So binary compression is done using base 64. Another challenge that we faced was MBCC conflicts due to high amount of write operations to upload parameters when appending to the same state. This is a common database thing when someone updates the state concurrently. There is a concurrency control conflict. So the optimization to that was the data model was modified so that every upload writes to a completely different key. And there were architectural fallouts like there was less endorsers in channels, level DB was not being used, and peers were deployed on the same node. So if we increase the endorsers in channels and deploy the peers on separate nodes, we gain high amount of optimization. Some experimental evaluation. If the number of contracts increase, the time taken to aggregate the parameter decreases. Over here for SignSGD specifically, if we have 48 contracts, the time taken to deploy is 500 seconds, but the time to aggregate on the chain is about 2 seconds, and for federated averaging it's 6.5 seconds. If the number of parameters increase, the time to upload parameters increase. However, the aggregation time remains the same. Over here, if the upload if the number of contracts increase, the upload time decreases. If the number of parameters increase, then the upload time increases. I'm sorry, in the first image over there, if the number of parallel contracts are increased. This tells us that with the current optimizations in place, we are able to achieve communication efficient federated learning over the hybrid blockchain setting. Performance of our attacker detection algorithm. We have independent and identically distributed setting and a non-independent identical distributed setting. Data is distributed uniform. So in the top image, the adversarial agent stands out very clearly. Data is distributed uniformly between the agents. In the non-IID setting, which is the bottom figure, agent 0 has a value of 0.78, which is clearly higher than agent 9, followed by agent 6, which is 0.67 and 0.65 respectively. Over here is an example of a Trojan introduced in a dog, which is classified as a horse. So this is the example we use to identify the Trojan. Security and privacy analysis. Since aggregation is done over the private blockchain, as long as 51% of the participants are honest, the average needed for the federated learning will be correctly executed. Privacy protection over the parameters is done with the help of channels, and each participant's privacy over the public blockchain is achieved with the help of hashing the parameters, and this is over the public blockchain. So in conclusion, we have a general federated learning framework that aims to deter adversarial attacks by providing accountability. The way it's general is because any aggregation function and any attacker detection algorithm can be plugged into it. The attacker detection algorithm for federated learning setting is designed against pixel pattern backdoor attacks as an example. And we have empirical evaluation for different settings and security and privacy analysis. What we plan to do in the future, we have a plan to develop Trojan detection algorithms for SignSGD. This seems to be challenging due to the communication involving only bits. The earlier we saw federated averaging. Still, we believe this is feasible by using more Trojan examples. We also plan to investigate integrating other federated learning aggregation systems into our system. Currently, we do only SignSGD and federated averaging. Here is the GitHub link and our emails. If you feel free to contact us about any information regarding the paper, and we'll be happy to provide it. Thank you very much.